Welcome to Statistics, where we bring complexity to clarity. I am excited to have you join me for our 6th unit, Mean, Arithmetic, Geometric, Harmonic, and Weighted Mean. Arithmetic mean, or simply mean, is the average of a group of numbers, or mean is the ratio of sum of observations to the total number of observations in the dataset. For example, if we have a dataset, say X with observations 1, 2, 3, 4, and 5, then the arithmetic mean, which is symbolically written as X bar, is equal to sum of all the observations divided by total number of observations, which is equal to 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which is equal to 15 by 5. Hence, mean is equal to 3. So, the arithmetic mean of the given data set is 3. Arithmetic mean is the most common and ideal measure of central tendency, as it satisfies almost all requisites of measures of central tendency. Let's see the properties of arithmetic mean in detail. The first one is the algebraic sum of the deviations of a set of values from their arithmetic mean is 0. For example, if we have data set X with observations 1, 2, 3, 4 and 5, your mean is equal to 3, and the deviation of each observation from the mean will be 1, minus 3, that is minus 2, then minus 1, 0, 1 and 2 respectively. Now taking the sum of deviation of each observation from the mean, which is equal to minus 2 plus minus 1 plus 0 plus 1 plus 2, which is equal to 0. Hence, in accordance with the property, the sum of deviation of each observation from the arithmetic mean is 0. The second property is the sum of squares of the deviations of a set of values from their arithmetic mean is always minimum. Now seeing the example. Again we have the same data set, suppose X with observations 1, 2, 3, 4 and 5. So mean is equal to 3 and deviation of each observation from the mean will be minus 2, minus 1, 0, 1 and 2 respectively, and the square of it will be minus 2 square, that is 4, 1, 0, 1 and 4 respectively. So the sum of square of deviation of each observation from the mean is equal to 4 plus 1 plus 0 plus 1 plus 4, that is 10. Now to understand the property in more detail, let's take another data point, say 4, that is other than the mean, and see the deviation of each observation with respect to it. So it will be 1 minus 4, that is minus 3, then minus 2, minus 1, 0 and 1 respectively. Taking its square, that is minus 3 square, 9, 4, 1, 0 and 1. And the sum of the square of deviation of each point from 4 will be 9 plus 4 plus 1 plus 0 plus 1, that is 15. As 10 is less than 15, hence from the property we can say that the sum of squares of deviations of a set of value from their arithmetic mean is always minimum. The third property is that arithmetic mean is amenable to further mathematical calculation. The first sub-property of it is let x1 bar be the mean of n1 observations, x2 bar be the mean of n2 observations, xk bar be the mean of nk observations, then the combined mean of capital N observations is given by x bar equal to n1 x1 bar plus n2 x2 bar plus up till plus nk xk bar whole divided by n1 plus n2 plus up till plus nk. Let's see it with the help of example. Suppose we have a data set, say x1 with observations 1, 2 and 3 Here the mean of x1 is 2 and number of observations of the data set is 3. And suppose we have another data set, say x2 with observations 4, 5, 6, 7 and 8, then its mean is equal to 6 and number of observations equal to 5. Now the combined mean x bar is equal to n1 x1 bar plus n2 x2 bar divided by n1 plus n2, which is equal to n1, that is 3 into x1 bar, that is 2, plus n2, that is 5 into x2 bar, 6, divided by n1 plus n2, which is equal to 6 plus 30 divided by 8, which is equal to 36 divided by 8, which is equal to 4.5. Hence, the combined mean of the two series is 4.5. The next subproperty is adding or subtracting a constant from each observation of a given series will add or subtract the same constant to the arithmetic mean. Let's see with the help of example. Suppose we have dataset X with observations 1, 2 and 3. Here mean will be 2. Now suppose we add a common constant A, that is 4, to all the observations. We will get x plus 4, that is 1 plus 4, which gives 5, 6 and 7 respectively. Now taking the mean of the new data set, it will be 5 plus 6 plus 7 divided by 3, which is equal to 6. So according to the property, the new mean is equal to the original mean plus the constant added, which is equal to 2 plus 4, that is 6. Hence we can see from the property. Similarly, you can subtract a constant from each observation and check the results. So from this, we can say that arithmetic mean is dependent on origin. That is, adding or subtracting a constant affects arithmetic mean. Seeing the third sub-property, that is multiplying or dividing each observation by a constant will multiply or divide the arithmetic mean by the same constant. Let's see with the help of example. Taking the dataset X with observations 1, 2 and 3, here mean will be 2, and now let's take a common constant, say A is equal to 4, and multiply all the observations with it. So 4 into 1 will be 4, 4 into 2 8 and 12 respectively. Calculating the mean of the new data set, that is 4 plus 8 plus 12 divided by 3, which is equal to 8. According to the property, the new mean is equal to the multiplication of the constant to the original mean, that is 4 into 2, which is 8. Hence, it is in accordance with the property. You can also check by dividing each observation by a constant. From this, we can say that arithmetic mean is dependent on scale. That is, multiplying or dividing a constant to each observation will affect the arithmetic mean. Let's see the merits of arithmetic mean. It is rigidly defined. It is based on all the observations. It is readily comprehensible. It is easy to calculate. It is amenable to further algebraic treatment. It is also least affected by the fluctuation of sampling. So these are the merits of arithmetic mean. Let's see its demerits. It is affected by extreme values. For example, if we have a data set with observations 1, 2 and 3, then its arithmetic mean is 2, right? And then taking the data set with 1, 2 and 96 as the observations will give the mean 33. So as we can see here, 96 is the extreme value which affects the arithmetic mean. So it is affected by extreme values. Next is, if there is large variation in the data, then arithmetic mean becomes sometimes meaningless. You can see in the above example also. It is not used to measure rate of growth or rate of speed directly. So these were the demerits of arithmetic mean. It is most popular and simple estimate and used widely in almost all the fields of studies such as social science, economics, business, agriculture, engineering, medical sciences, and other sciences. Example for agriculture can be average yield of wheat or average seed rate, etc. Methods of computation. Arithmetic mean can be calculated through various methods. For raw data or ungrouped data, it can be calculated using direct or assumed mean method. And for grouped data, through direct, assumed mean or step deviation method. We'll be seeing them in detail now. So raw or ungrouped data, the direct method formula will be arithmetic mean is equal to summation I is equal to 1 up to n xi divided by n, where I is equal to 1, 2, 3 up to n observations and x is equal to variable value. Assumed mean method. X bar is equal to a plus summation I is equal to 1 up to n di upon n, where di is equal to xi minus a and a is equal to assumed mean. For grouped data, direct method, arithmetic mean is equal to summation I is equal to 1 up to k fi xi divided by n, where fi is the frequency of ith class, xi is ith class mid value and k is number of classes. Assumed mean method. X bar is equal to a plus summation I is equal to 1 up to k fi di upon n, where di is equal to xi minus a and a is equal to assumed mean. Then step deviation method. X bar is equal to a plus summation I is equal to 1 up to k fi dxi upon n into I, where dxi is equal to xi minus a upon I, where I is equal to class interval. Now let's see geometric mean. It can be abbreviated as GM. It is defined as the nth root of the product of n items of a series with following relation. For raw or ungrouped data, geometric mean is equal to nth root of the product of x1, x2 up till xn, which is equal to x1 into x2 into up till into xn, whole raised to 1 upon n. It can also be written as antilog of summation I is equal to 1 up to n log xi divided by n. And for grouped data, geometric mean is equal to capital nth root of the product of x1 raised to f1, x2 raised to f2 up till xk raised to fk, which is equal to x1 raised to f1 into x2 raised to f2 into up till into xk raised to fk whole raised to 1 upon capital N. It can also be written as antilog of summation I is equal to 1 up to k fi log xi divided by summation I is equal to 1 up to k fi, where k is equal to number of classes and summation I is equal to 1 up to k fi is equal to capital N, that is total number of observations. Now let's see the merits of geometric mean. It is least affected by the extreme values. It is based on all the observations and it is suitable for further algebraic treatment. So these are the merits of geometric mean. The demerits of geometric mean are its calculation is somewhat complicated. It cannot be calculated if any of the value in the set is 0. If any one or more values are negative, either geometric mean will not be calculable or an absurd value will be obtained. So these were the demerits of geometric mean. The uses of geometric mean. Arithmetic mean gives equal weightage to all the items and has got a tendency towards higher values. Sometimes it is necessary to get average having a tendency towards lower values. In such cases, geometric mean is helpful. For example, averaging the ratios of change, average of proportions, etc. Now, let's see harmonic mean. It can be abbreviated as HM. Harmonic mean is the reciprocal of the arithmetic mean of the reciprocal of the values of a variable or series. For raw or ungrouped data, harmonic mean is equal to n divided by 1 upon x1 plus 1 upon x2 plus up till plus 1 upon xn. That is n divided by summation I is equal to 1 up to n 1 by xi. And for grouped data, harmonic mean is equal to capital N divided by f1 upon x1 plus f2 upon x2 plus up till plus fk upon xk. That is summation I is equal to 1 up to k fi divided by summation I is equal to 1 up to k fi by xi, where k is equal to number of classes and summation I is equal to 1 up to k fi is equal to capital N, that is total number of observations. Now let's see the merits of harmonic mean. It is based on all the observations. It is good mean for highly variable series. It gives more weightage to small values and less weightage to large values. As divisions and ratios are involved, so when we divide a larger quantity, that is 1 upon 10, it will give us a decimal place 0.1. Hence, this. It is better than weighted mean since in this values are automatically weighted. So these are the merits of harmonic mean. Demerits of harmonic mean. Its calculation is complicated. It cannot be calculated if any of the value in the set is 0 because division is involved. So 1 upon x1, and if x1 is equal to 0, then 1 upon 0 gives us infinity. So it cannot be calculated if any of the value in the set is 0. Its value is generally not a member of the series. Uses of harmonic mean. It is used in time series data, for units purchased per rupee, kilometers covered per hour, problem solved per time, etc. Relation between arithmetic, geometric and harmonic mean is geometric mean is the root of product of arithmetic and harmonic mean. It can also be written as the square of geometric mean is equal to product of arithmetic mean and harmonic mean. Also, arithmetic mean is greater than equal to geometric mean greater than equal to harmonic mean. Weighted mean. When different observations are to be given different weights, arithmetic mean does not prove to be a good measure of central tendency. In such cases, weighted mean is to be calculated. So if x1, x2, x3, xn are different observations and w1, w2, w3, wn are their respective weights, then weighted mean is equal to w1x1 plus w2x2 plus up till plus wnxn divided by w1 plus w2 plus up till plus wn, which is equal to summation I is equal to 1 up to n wixi divided by summation I is equal to 1 up to n wi. If all the weights are equal, then the weighted mean is same as the arithmetic mean. Merits and demerits of weighted mean. Weighted mean is similar to arithmetic mean, hence its merits and demerits are same as that of the arithmetic mean. Uses of weighted mean. It is used when the number of individuals in different classes of groups are widely varying. It is used when the importance of all the items in a series is not same. It is used when the ratios, percentages or rates, for example rupees per kilogram, rupees per meter, etc. are to be averaged. And weighted mean is particularly used in calculating birth rates, death rates, index numbers, average yield, etc. Thank you for joining me on this journey through our 6th unit mean, arithmetic, geometric, harmonic and weighted mean. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity to statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.